Hello, everybody. So we're going to talk today about, clean up piece of paper, about mass spectrometry. So what mass spectrometry is it's a study of the mass of a molecule. Essentially, it's analyzing the mass of a particular molecule, but not only that, it's a molecule broken into fragments. So we'll talk about it in a second. Before I get there, I want to talk about the difference between spectrometry and spectroscopy. So anytime you see something that says spectroscopy, this is usually referring to something that has to do with light, or another way to think about it, the electromagnetic spectrum. So magnetism, etc. Anytime you have something in the electromagnetic spectrum, it says spectroscopy. Everything else are usually going to be called spectrometry. Okay, and both of these things, when you run them, like if you were to run a UV spectroscopy and analysis, you'd get a spectrum. So spectrum is singular, but if you get multiple of them, they're called spectra. Okay. So if you have a whole bunch of, you run an analysis and you get a whole bunch of different spectrum, we'd call those spectra. Okay, just some things to get out of the way in case you move on in your chemical career. So down to how this works. Okay, so let's say you have a molecule that looks like this. And you want to analyze, but you don't know what it is. Let's say you have no idea what this molecule is, but you're going to run it through a mass spec and you're going to see what results you get. You're going to see if you can get a spectrum. So how this works is, I'm just going to draw a foot here because that's how I like to think about it. It kicks this molecule with a certain amount of kinetic energy. Okay, a very specific amount of kinetic energy. And kinetic energy is based on speed and mass. So what happens is, because if you have a whole bunch of different components, depending on their mass, they get separated. Okay, so this thing is going to break into fragments. Sometimes it doesn't, sometimes it does, but it's going to travel way down a tube. It's going to break into fragments. Where it breaks depends on the most substituted spot. So hopefully you agree that this here, this carbon right here is tertiary, well, it's quaternary currently in nature. And so that's where it's going to break. It's going to break at the most substituted spot. Now, it can technically just go down as one whole piece. So you'll probably get something that looks like this. Okay. But it's in the process of this, it's going to lose a hydrogen somewhere. And so it'll have like a positive charge somewhere. So let's say it lost a hydrogen there. So this whole piece might make it all the way down. But more likely, it's going to break this here and here. And so you'll get a piece here, okay? And it will also lose a hydrogen where it breaks. And a piece here. Now this carbocation right here is why it breaks right there, because remember, carbocations are more stable if they're on primary, secondary, or if they're on tertiary than they are secondary than they are primary. So tertiary is going to be way more stable than secondary, which is going to be more stable than primary. So this is tertiary, so this is more stable. And that's why it broke there. Okay, it wouldn't break like here, or it wouldn't break here, because then you'd have primary carbocations. Okay, so I want to give you an idea of kind of what flows down the tube once it's kicked. And now we're going to talk about what you might see as a result of this. So the spectrum will give you something that looks like this. And the numbers might go from 0 to, let's say, 100. And the units on this will be m over z. That's mass to charge. Now, the beautiful thing about all these alkanes that we're doing is that the mass is going to change depending on what alkane there is. It's talking about the molar mass. But the charge will always be a 1+ charge. Okay? The reason it will always be a 1+ charge is because we're always just removing like one hydrogen from it. And therefore, you'll have a 1 plus. I really shouldn't even say you're removing one hydrogen from, you're removing a bond from it is a better way to think about it. So you're removing bonds from it. And when you break a bond, you take away electrons, you have a positive 1 charge. So this will always be 1 plus. Anything divided by itself is always whatever that thing was. So this is pretty much more or less just the mass. Now you will run into situations where maybe this is a 2 plus or a 3 plus in other classes, but in this class, we're always just talking about alkanes, so it will always be just a 1 plus. Okay, now let's talk about what you'd see here. So when it comes to organic chemistry, it's pretty fun because especially for those who don't like math as much, because we don't do very much math in organic chemistry. Let me show you. So if we were adding up the mass of some sort of alkane, carbon is 12.01 and hydrogen's 1.008. But in organic chemistry, we just say, dude, that's 12 and that's 1. Okay, so carbons and hydrogens, 12 and 1. Okay, so let's go ahead and go through and see what this might actually produce in a real mass spectrum. The first thing you'd want to start with is the mass of this actual fragment. Okay, so the mass of a fragment that goes through unbroken, and I'm actually going to take this positive charge off because you will end up with the mass of the entire fragment going all the way through, is going to be 1, 2, 3, 4, 5, 6 carbons, which means there must be H14. So the full mass of this thing would be based off of 6 carbons and 14 H's. In other words, the mass would equal 6 times 12 plus 14 times 1. What was that? 72, 82, 86. So you would have a peak that would come right about 86. And we would call that peak the molecular ion peak. What that is that's the overall mass of the thing. Then you would have another peak at m plus 1, so 87. The reason you have another peak at m plus 1 is because of isotopes. So hydrogen sometimes has an isotope that has a mass of 2. And so if you have a fragment that goes down that has one of those hydrogen isotopes that's got a mass of 2, it will add 1 to the overall mass of the thing. So this is always going to be very tiny. But it will always be, and it's tiny because there aren't very many of those isotopes, but it will always be 1 higher than the mass of the molecule. The next thing you'll see to give you structural information will be peaks for these main fragments. Okay. This one is made of 2 carbons. And then let's draw it out just to make sure we're comfortable with this. There's 1 hydrogen there, 1 hydrogen there, 1 hydrogen there. Okay. And then when we broke this thing apart, right? Hopefully you agree there's a hydrogen there and a hydrogen there. And then we broke it apart, right? Same thing still occurs. So same thing happens. There was no hydrogen here. So when we broke it apart, there's a hydrogen there and a hydrogen there. That's these two. Let's make that one blue. Let's make this one purple. But there's nothing else there, okay? So this carbon has 3 bonds and no other electrons there. That's why it's a positive charge. So this thing is C2, but it has 5 hydrogens, telling us 2 times 12 plus 5 times 1 would give us the mass of this thing. That's 24 plus that is 29. So at 29, you'd have a peak. Okay. So that's this fragment, and then we'd also still have this fragment over here. We'll kind of do the same thing. On this piece, there were no hydrogens. It was quaternary, right? So you had that carbon there, and that carbon there. That's this carbon there, and that carbon there, respectively. And if we were to add up the mass of this, there are 4 carbons, and then there's 3 hydrogens on each one of these carbons, and there's nothing on this one. Okay, so it'd be H9. And you can count it again if you want to, 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, and you get this. So 4 times 12 plus 9 times 1, that's, what is that, 48, 57? So you'd also have another peak at 57. Now that peak at 57, because this was really stable, will actually be bigger because you made a little bit more of it. That many times, the biggest peak is the base peak. It tells you kind of the most stable fragment. Sometimes the base peak is the molecular ion peak. They're both really big. But usually it's just the most stable fragment, okay, or the thing that there was the most of. And again, that was at 57. Now there will be lots of other little peaks. The reason there's lots of other little peaks is because that kick doesn't guarantee it's going to break right there. Sometimes it breaks here, 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 here. So you'll get like lots of little like crazy little fragments and stuff like that, etc. But this base peak will always be the biggest. The M+1 will always be the tiniest one that you start with here, and the molecular ion will always be the M+1 minus 1, which tells you the mass of the thing. Okay, so let's go ahead and take that information and start on our lecture now. Here's a picture of the mass spectrometer. Great. So essentially it hits it with electron beam. That electron beam breaks those bonds, causing it to be now positively charged, and then you can use a magnet to both draw and repel those fragments down this way, essentially through the analyzer tube. The positively charged ions get deflected according to their mass to charge. So here's where they start to kind of separate. So an example of how they separate would be, you can imagine if I were to kick like maybe a box of balls right here. So I'm going to turn the box on this side. And let's say you got a bowling ball, you've got golf balls in here, and you have like a, maybe a wiffle ball, okay? And you gave this thing a kick as hard as you could. I hope you agree, like the wiffle ball, this one, would fly. I didn't draw very to scale. The wiffle ball would fly. Whew, it's so light, right? And then the bowling ball would be like, do, 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 just like slowly going down. And the golf ball would be somewhere in between. Because based on their mass to charge ratios and based on their mass, they separate at a different rate, because even though you kicked it with the same amount of energy. Okay, so they'll go down the tube, this one will be analyzed, then that one, and then you'll get your results. Okay, so essentially that's what this is saying. Okay, so it shows you, here's what's going to happen. You'll have a molecule, you can measure the molecule, but then you're going to lose an electron, and you get this this unstable radical carbocation. And then it says, hey, it's going to break into these, and then the cations, those positively charged parts, are the ones that are analyzed. The radicals are not. And it walks through a little more of how they're broken down. Like if you had a CH4 and you happen to break it, then you'd get a CH3. And if you broke that, you'd get this and this and this. And this kind of explains why you have these tiny little fragments all over the place, as you can see in this mass spectrum right here. So this first one is giving us an example of hexane. So I'm just going to kind of reiterate everything that we just said, just to make sure we're on the same page. Okay, hexane's formula is C6, and because it's all single bonded, you can actually figure out the number of hydrogens if you remember 2 times that number plus 2. 2 times 6 plus 2 gives us 14. And if we're analyzing the mass of this, that's 6 times, what's the number? 12? I can do it, plus 1 times 14, which would give us 86. So the mass of this one fragment of C6H14, which would look like that, 1, 2, 3, 4, 5, 6. The mass of this whole fragment is 86. this would be our 86 peak right here. Again, we call that our molecular ion peak. Then there's the M+1. In the M+1, that's where you have the little tiny, tiny peak that you see first. That's at 87. Then the most stable fragment is going to be this base peak at 57. So let's see what the base peak was. Let's try to break this down and figure out where it got cut and which one is the most stable fragment. Because at 57, what that most likely means, I'm kind of just doing some math right here. That means we probably had 4 carbons, because if we had 5 carbons, that would be 60. So that's not going to work. So we had 4 carbons, then that would be 48. And then you'd have to have 9 hydrogens, which makes sense because it's very much like this one that we just did. 4 carbons and 9 hydrogens would give us 57. So it broke somewhere, 1, 2, 3, 4, right there, where it had 4 carbons and 9 hydrogens. So that happened to be the most stable fragment of this thing, is that one. Okay. So it gives us little contextual clues. You could find out this mass and that mass, and it would be various fragments. This looks like it was 3 carbon C3H, let me think, H6, right? And then etc. Or C3H7, excuse me. And then the next fragment would be 1 more down with the C2. All right, so overall, the main thing is I want you to understand M+1 peak is the mass of the molecule you're analyzing, +1. The molecular ion peak is the mass of the molecule you're analyzing, period. And the base peak is going to be generally the most abundant fragment, which is most often the most stable fragment. Let's look at these two. Well, I guess we can do this. It says label the molecular ion and the base peak and the M+1 peak. So the M+1 is always going to be the most tiny one. There. Then the one next to it has to be the molecular ion peak. Then this biggest one has to be the base peak. Now let's see if that makes sense for pentane. So pentane is C5H12. If we didn't know that, again, we know C5 would be pent. And then times 2 plus 2 would give us H12. So it's saying 5 times 12 plus 12 times 1 would give us the molar mass of this thing. This would be 60 plus this would be 72. And lo and behold, look exactly where we find this molecular ion peak. It's at 72. The base peak tells us where it fragmented. It looks to me to have the base peak was when you had possibly 3 carbons. Okay, let's look at these two. It said pent 1-ene and pent 1-ine. Pent 1-ene would be this with a double bond at the 1 carbon, and pent 1-ine would be a triple bond at the 1 carbon, like this. If we were trying to figure out the formulas of each of these respectively, hopefully you agree there are 5 carbons. But now we would say it was an H12, right? If it were all alkane. But anytime you have a double bond, that's called a degree of freedom. We're going to take away, or a degree of saturation, we're going to take away 2 of those hydrogens. So instead of saying H12, it's H10. So to give you an idea, up here, when we had the pentane, it was all alkane, it was H12. You add a double bond, it becomes H10. You add a triple bond, hopefully you can already see it, it's going to be H8. All right. Now let's go ahead and see if we can figure out which one's which. though you can probably guess based on this one has 2 higher things, but we know that C5 gives us 5 carbons and then 10 hydrogens, which would be 70. And here, this would be 5 times 12 carbons plus 8 times 1 hydrogens, which would be 68. So you tell me which one's which. Hopefully you agree that this one pent1-ine belongs over here because its molecular ion is 68, and this pent1-ene belongs here because its molecular ion is 70. This is just more of the same, showing you how each fragment was produced and made each major peak. And that's about it for mass spec. So this question that you got here, if you understood this, is probably about as complicated as it's going to get, though I might have something that has more of the one we kind of started with, and ask you to identify where it fragments. Again, you're always going to look for the more substituted spot. That's where it would fragment the most. Okay, now we're on to the next portion. The review of electromagnetic radiation. So, let me get a piece of paper. I'm going to go a little bit crazy here, and I'm sorry, but let's go crazy. Why not? You can always fast forward. Okay, crew, so let's start with kinetic and potential energy. So if I have a, let's say I have a pen, okay, and I'm going to throw it at you. Whack. Okay, I'm going to throw it like across the room at something. But let's say it's not a pen, it's another object. Hopefully you agree that that how fast I throw it and the mass of this object would be the two variables that affect the amount of pain I could inflict on somebody. So like if I threw it really fast, or if I threw like a bowling ball versus a cotton ball, the bowling ball would hurt and the fast thing would hurt, right? That's because kinetic energy is based on mass and velocity. So the amount of energy that an object has is based on how heavy it is and essentially how fast it's going. All right, then we have this other thing. It's called potential energy. And you don't need to know these equations. PE, or potential energy, so let's say I have an object and I'm going to drop it on my hand. Okay, I don't know what the object is, but what would make it hurt more on my hand? Hopefully you agree how high I drop it from, right? If I drop it from like the Empire State Building onto my hand, that would hurt a lot. And the mass of the object. So if I dropped a bowling ball versus a cotton ball in my hand, those would inflict 2 different levels of pain. And that's because potential energy is in fact based on mass, mgh, times gravity, which you cannot control. It's just an acceleration, how fast something speeds up as it falls, times height. Okay. So the mass and the height are the things that make a difference that you can actually control. Okay, kinetic energy is movement energy, and potential energy is stored energy. So when you think about stored energy, think of battery, think you have like, let's say a well filled with a bunch of water, or one of those water towers filled with a bunch of water. It's just got stored water in there dying to get out. Or think about something that I'm holding like this above something else. So here it's potential, and as it falls, it becomes kinetic. All right, so that's what we're going to focus on right now. If you have a pen or an object and you lift it up really high, Okay, so let's say I'm holding that object here. If it took me 15 kilojoules of energy to get it up here, once it's up here, I have 15 kilojoules of potential energy. Okay, so as I'm just holding it, it's got 15 kilojoules of potential energy. But once you let it go, it starts falling. And just before it hits the ground, it's got 15 kilojoules of kinetic energy. Okay, so up here it's potential, and just before it hits the ground is 15 kilojoules of kinetic. Why? Because it transferred from potential, where it's just stored, to kinetic, where it's actually movement energy. So if I ask you what's happening right here in the middle, what's happening is that the stored energy amount is going down as the kinetic energy amount goes up. So just whoosh. So right here, it would be 7.5 potential energy and 7.5 kinetic energy. Cool. And all of what I've just taught you is absolutely pointless, except for this one idea. The reason I teach you this is to show you that energy is just being transferred from one thing to the other, from potential to kinetic, etc. But my question to you is, what happens when it hits the ground? Watch my pen. What happened to the energy? I'm gonna do it again. Where'd the energy go? Because now it doesn't have any height, it doesn't have any potential energy anymore, it doesn't have any kinetic energy, it's not moving. We know that it had 15, it should have 15. What the heck happened to the energy? Well, some people say, oh, you put a thermometer there, you can measure a little bit of heat. Yeah, you can. Some of it went into the table as vibrations, that's true. But the main thing that came off of it was, listen, sound. So as soon as it hits the ground, it lets out a sound wave. Sound is energy. In fact, the way I like to think about this is this morning I had a latte for breakfast. It was delicious. That latte gave me energy that is fueling me to do this talk right now. That latte gave me energy to lift up this pen and drop it. That pen, essentially, if you were in the room with me, went into your ears and made your ear hair wiggles. Ear hairs wiggle. So your little cilia in your hair or in your ears went because of my latte. So my latte made your ear hair wiggle, which is really, really crazy. So given that idea, let's talk about why the heck I even introduced this. Well, because this is how light works. If you have an atom, you should probably already know this from Gen Chem 1, but you have these discrete energy levels within the atom where electrons can fall. So if this is a carbon atom, you'd have 6 protons in the center, you'd have 6 electrons chilling outside, and what happens is, if you have an electron and you excite it, let's say you shine light on it or heat it up in a certain way, you can bring that electron up here. That's like lifting the pen up. And then you let go, it falls like this, hits the ground, and lets off this wave. That wave is what we know as light. So here in the real world where we can see things, they're more tangible, it's all the real world, but where it's more tangible, when you drop this, it let out a sound wave. But when an electron falls, it lets out a light wave. And we call that light wave a photon. Okay. Now there are other ways that this can happen. And there's different energies that can occur. So if I drop that electron drops from really far, you can let out a high energy light wave. If over here you drop a pen from really high up, you're going to have a louder sound, right? And that's kind of the principle. That's why I showed you this, because I think it's really connected to this. Okay, so some other things to think about is the kind of wave that it lets off. So when you let off a light wave, again, I said depending on like how high that electron falls, you'll get different energy levels or different energies. So you might let off this. You might let off a light wave that looks like this. Or you might let off a light wave that looks like that. Cool. So let's look at these 3 different light waves. The distance between here and here is called the wavelength. It's the length of the wave. So any two identical parts, we call those the wavelength. So this one, I hope you agree, has a bigger wavelength than down here. So this one right here has the highest wavelength. We usually denote that with lambda, but I don't think we'll talk about it. I just want you to know it. The general idea. Okay, this one would have a smaller wavelength. Frequency, however, is how many times you see the wave. Okay, so this one, based on one wavelength here, you only see it like 2 times, right? 2.5. Here you see 1, 2, 3.5, and here you see 1, 2, 3, 4, 5, 6. So this one you see it more frequently. You see the wave more frequently under a certain distance. So this one has a higher frequency. So frequency is oftentimes denoted with hertz, inverse seconds, or you can even say 1/seconds. And yet still none of what I'm teaching you matters, but it does connect. So let's say that we put a boxing glove on top of all of these. This is why I was not an art major, okay? In case you've seen my chair conformers, you know that. Okay. Light, one of the really cool principles about light is, assuming it's in a vacuum, it travels at exactly the same speed every single time, 3 times 10 to the 8 meters per second, no matter what. Okay, so these are boxing gloves, so they're going to and all these again are traveling at the same speed. This is your face. Okay, you're going to get hit with all these boxing gloves, right? So if we look at just the top one, it's going to hit you. It goes boom, boom, boom. Okay, ouch. You got hit 3 times. That stinks. If you get hit with this one, it's boom, 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 boom. I just did too many. It's 4. But if you get hit with this one down here with a high frequency, it's boom, 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 and you're knocked out. You're gone. Goodbye, you. Okay, so this one down here hit you more frequently, and the reason for that is it had more energy. And now we're getting into why I did this whole thing. This high frequency thing has more energy in it. And if you have more energy, you can do more damage. Okay. So I wanted to explain to you what we'll eventually get to here. Now, wave number is essentially equal to 1/lambda. So it's the inverse of lambda. So if you remember, if you have a high frequency, you have a low wavelength. So in organic chemistry, we take 1/lambda and we call it a wave number. Why? Because we want to mess with you. So if you have a high energy thing, that means its wave number is going to be high. The inverse of its wavelength will be high. Okay. This is also proportional to frequency. Okay. Or I should probably let you know that this is frequency. Okay. So instead of saying frequency, because it's really technically 1/lambda, we give it a little tilde right there. And we say wave number is actually a little tilde. Okay. So we'll get to that point here shortly. But hopefully that was a fun little intro to this. All right, so organic chemists specifically use infrared spectroscopy. Infrared spectroscopy is where electrons, I said that the electrons fall, specifically where they fall to an n equals 3, 4, or 5 level. So if you were looking at an atom, it would fall to the 3, 4, or 5 level. Okay. So what happens when a molecule absorbs light, IR light, is it can actually make that molecule wiggle. Because remember, this is energy. IR light is energy. So if a molecule absorbs IR light, the bonds can stretch and go like this. And even if you have like 2 bonds between here, like water, in this case it looks like, I don't know, some kind of carbon, fluorine, two hydrogen thing. It goes like this. It can bend, it can stretch, they can scissor, they can do all sorts of really cool wiggling. And in fact, there's an entire course that exists on how bonds wiggle when they absorb energy. It's really actually kind of interesting. Okay, so if you have a molecule and you shine light on it, it stretches, moves. Okay. Why this is important isn't even so much why we're learning this right now, is because it actually affects kind of your day-to-day life. Let me explain how. If you have, let's say, carbon dioxide in the atmosphere, or methane, which are greenhouse gases. And the reason I'm going through this is because most people get all the way through their college career now without even knowing what climate change is or how it works. So these are greenhouse gases. You could also have this. Methane is a pretty big one. It's actually wiggles a lot more because there you can do the bending we talked about, and this CO2 just usually stretches. But with methane, you can do bending. So it absorbs a lot of energy. And this is the sun. The sun shines down onto these molecules. The sun releases a lot of IR light. So the waves travel, the light waves that we talked about that have energy, and they essentially beat the crap out of these. Think about them with little boxing gloves. Boop, 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 boop. These molecules get boxing gloves hit on them, and they're like, whoa, whoa, whoa. They do this. And these guys bend. They're whoa, whoa, whoa. They get smacked around, okay? So that doesn't seem so bad, right? Until you think about what temperature is. If you've never thought about what temperature actually is, temperature is a measurement of kinetic energy. I need to rewrite that. Of molecules. So if molecules have a lot of kinetic energy, if they're moving around, if they've absorbed a certain amount of heat and they're moving around a lot, then they have a high temperature. So here, this is exactly how essentially climate change works. The sun comes down, it heats these up, they start to wiggle, boom, that is the temperature increase in and of itself. So the more molecules we have in here, the hotter the atmosphere is. When the atmosphere is hot, here's the ocean. The ocean has a bunch of dissolved CO2 in it. So picture all these. This is the beautiful ocean. Okay, here, let's draw a palm tree. Let's make it nicer. Cool. Beautiful palm tree. If you've ever heated soda up, you know that it gets flat, right? So not only is the atmosphere hotter now, as the atmosphere gets hotter, the dissolved CO2 in the ocean comes out, just like it would if you were to heat up a soda. And it adds even more to the atmosphere. So it creates this cascading effect of temperature, warmer temperatures rising. And that is the principle behind how global warming is working. Okay, so I think that's important for you guys to know because you're a scientist and you should trust science. Or not even trust science, question it and prove it to yourself. Okay, so now it asks, which of the following has a higher energy? Something with a wave number of 3000 or something with a wave number of 1500. Hopefully you agree that 3000 has a higher energy because we said that wave number is proportional to energy. But here it talks about wavelength. If you remember, wave number is 1 over wavelength. So wavelength, 1 over wavelength is proportional to energy. Or you could just think about it as wavelength goes down as energy goes up and vice versa. So here, if we have 10 microns or 20 microns, it asks about which has a higher energy. Higher energy is going to be the lower wavelength, the one that had the most boxing gloves on it. Okay, so how IR spectroscopy, because we're dealing with light, works is essentially you have a molecule and you beam IR light through that molecule. And like we said, things wiggle. So a lot of the energy gets absorbed and some of the energy gets transmitted. These big peaks right here are where the energy was absorbed. Okay? And the empty space are where light just went through the sample. So this molecule, whatever molecule this was, wiggled right here. It also wiggled here, and it wiggled here, and here, and here at those different energies, but it didn't wiggle very much here or here. Light just went right through, and the molecule couldn't care less. So what that allows us to know is what was in the molecule, because we know specifically if we shine light at an OH bond, for example, it's going to have this really broad area where it absorbs energy. And CH, same thing. This area is called the fingerprint region, this whole spot right here. And this depends on each individual molecule. It's a lot harder to analyze this area, so we don't care. But from 1500 on, we do care, okay? And this is where we're going to kind of stick. Okay, let's go ahead and compare the functional groups here and here for these two molecules. So let's say you put both of them in, or let's say you're trying to turn this one into that one. You wanted to see if you were successful. You'd run an IR spectrum on each of them. And sure enough, in the non-fingerprint region, this shows a C double bond O, but so does this one because they both had a C double bond O. This one had CH, no problem. But the fingerprint region itself was different. So you got two different molecules, even though these peaks were very, very similar, because they both had a C double bond O, they both had a CH, and there is no real C to O area, and we'll see that in a second. All right, so we were here already when I was talking about increasing energy in wavelength or wave number. Here's where you usually see things. So lighter atoms have a higher frequency. You can prove this to yourself by tying a really light thing onto something, like let's say a yo-yo. And with a yo-yo, you can have it go up and down and up and down and up and down. But tie a string to a, let's say, bowling ball and try to make that sucker go up and down. It doesn't have a very good frequency in terms of how it goes. So lighter atoms have a higher frequency because they can stretch more. You just think about them having like a spring between them. Stronger bonds also have a higher frequency. So if you have, trying to think of how I could put that. I think the best way to think about it is the fact that stronger bonds are just generally higher in energy. And if they're higher in energy, they're going to be higher frequency. And then we have these single bonds down here, like I told you, C to O, you don't really see it. It's because it's in the fingerprint region. This, or very similar, is what you'll be given on the exam. I said memorize. Congratulations, I don't care. The main things that you're going to want to notice is the OH. Again, that's that really broad stretch we looked at. So if a molecule has OH, it'll do this. It'll have an area from here to here, and it talks about the intensity. It's got a C double bond O or C double bond C. You can see how they all kind of relate. C triple bond to a C and C triple bond to an N come out exactly the same. It's really hard to determine which of those it is. So IR spectroscopy is just another clue or another tool in our toolbox. You could also use NMR after this to figure it out. Okay, so it said, which of the following absorbs at a higher wave number? We already said the stronger one is going to be the higher energy, and we know higher energy is a higher wave number, but we can go over here and see as well. I think it's kind of important that we do. Start getting to use this table. So it's essentially asking us to compare this one to this one, a C double bond or C triple bond. And you'll see the C double bond is in fact at a lower one, and the C triple bond is at a higher one, once again, because this is stronger bond. So it's a stronger bond, but also the table tells us. Now it says compare, or which compound, A, B, or C, do you think gives rise to this spectrum? This is going to be fun. Let's go through each one. Hopefully you agree they all have alkanes. Okay, it's all got carbon-to-carbon bonds, single sp3 carbon bonds. Let's look at the differences. Both of these have a carbon-carbon double bond, all three of them. So let's go ahead and look at where a carbon-carbon double bond is, just so we can kind of get used to it. It's the 1650, and it should be about a medium thing. So we go over here, if this is 1500, this is 16, this is about 1650, and we got a medium peak. This right here is a carbon-carbon double bond. Okay, all three of them have it. Now let's go look at the next thing. The next thing that this one has, this one doesn't, is a carbon to oxygen double bond. So let's go look at this. A carbon to oxygen double bond should be around 1700, and it should be strong, meaning it goes all the way down. So let's look over here. Let's look for 1700. If that's 15, 16, 1700. So I'm at 1700. It's to the left of this thing. And I don't see any strong bond. Do you see anything strong right here? Right? It would be like going down here. That's probably not our thing, okay? Because a carbon double bonded to an oxygen at 1700 is not there. Then we have this one, which has an OH. If you remember that OH is this broad spec thing right there, you'll remember it for the rest of your life if you're an O-chemist. But 32 to 3600, so right here to right here, should be that big, broad stretch. And that's not there either. So it should be 600 to 3200 inverse centimeters for an OH stretch. And that is not there either. Therefore, that's the only answer that works. Okay, so if you're trying to deduce which one's which, just kind of go through each one methodically and see. These are all the sp3 hydrogens, carbon to hydrogen bonds, which fall about 3000 to 2800. So you're fitting right in that range. So in case you're wondering what these peaks are, these are carbon to hydrogen bonds, sp3 and a couple sp2s. Says which type of bonds are responsible for the absorptions in compounds A and B. So I'm just gonna, let's just pull this off. So in compound A, again, I have that 28 to 3000. They're medium, they're not super down here. These are carbon to hydrogen bonds. sp3, maybe, no, I don't even see sp3 or sp2, I just see sp3. So this looks like it must be all alkane. And then we have this sucker right here. Remember, the fingerprint region we don't care about. But this one right here looks to be about 1700, and it looks to be pretty medium or even strong. It goes down there quite a way, so I'd even call that one strong. So we look for 1700 strong. Oh, dude, look, often at 1700. Carbon double bond oxygen. So this is probably a carbon double bond oxygen. Same thing over here. We got the carbon, the sp3 hydrogens. But over here, that's 20, 21, 22, 2250. There's a really strong peak there. It says these are medium, but yeah, I don't see any difference. I would still call this kind of strong, but due to the fact that we don't have any other information, it's going to be a carbon triple bond to a carbon or carbon triple bonded to a nitrogen. We're not sure which one, or maybe it's both. Okay, I think we covered enough. I think you guys can go through and do this on your own. This would be the 3200. This would be the carbon double bonded carbon at 1650. This would be the carbon at about 1700 double bonded to an oxygen. So I think, I guess I did just go through the answers real fast, but yeah, I think that was a long enough lecture for me. Hope it was a long enough lecture for you, and we learned about global warming. All right, crew, have a great day.